you read a homework problem or a quiz problem or a test problem, and you see the word compressor, and you think, okay, where do I go from here? What would my sketch look like? Uh, where where might I go from there once I got my sketch? What I like to do is give you some tips on how to approach attacking a compressor problem. I'm going to follow the same recipe as I did for turbines. What I want to do is show you some real world equipment that are compressors, show you what your sketch should look like, and then show how can the continuity equation help you solve your problem, and how can the first law of thermodynamics help you solve your problem. And those two fundamentals, they're the same for turbines and compressors and lots of other equipment. So the fundamentals are the same, but you just might use them differently, or you might evaluate properties differently. So let me give you some tips on compressors. This is an industrial scale centrifugal air compressor. And I've got some experience starting up one of these large scale compressors in a production facility where I was a thermal systems engineer. So we've got outside air coming into this air compressor. It's a single high-speed rotating rotor, pretty large inlet area for air. So the rotor is spinning around, and out comes the compressed air at a higher pressure, and off it goes to various processes that need a supply of compressed air to operate. Now, on my sketch, I'm showing a big red arrow going out and W dot. Well, this is the electric motor drive to this centrifugal air compressor. Why am I showing that arrow still going out? Because I'm showing W dot out is less than 0. So my sketch on top of this image shows the electric motor drive is providing power to the compressor, but I'm trying to stay true to my problem-solving skills where I'm always showing W dot out in my sketch arrow. So we've got ideal gas, the ideal gas air. Your instructor is going to give you some guidance on whether to treat the ideal gas air as having constant specific heat or variable specific heat. And you'll be able to talk about those kind of decisions in your class. This is a great cutaway view of a multi-stage centrifugal compressor. And so let's see what we can learn by looking at this. Here's our inlet gas. It could be air or some other gas, inlet into the center of the first rotor. The rotor spinning around at high speed, and then this is the discharge of the first stage, and then it admits that it discharges there into the center of the next stage. More spinning around, higher pressure coming out, going into the next stage, and the next stage, and the next stage. So you get the idea that compressed air or gas is coming out here through multi-stages. Now, what else can we learn by looking at this? Let's look at the discharge areas of each stage. Notice how they get smaller and smaller. That's our clue that the specific volume of the gas is decreasing, lower specific volume. Now, common sense tells us that the pressure is going up. It's a compressor, for heaven's sakes. So pressure is going up, specific volume is going down for a compressor. Here's another type of compressor that's called a scroll compressor. This application would be for compressing refrigerant. In this case, I'd say, oh, it's going to be a phase change substance. For example, refrigerant R134A could be coming into this scroll compressor as saturated vapor, and it would be leaving as a superheated vapor. And most of the space in this large cylinder is the electric motor drive. And you might find this piece of equipment outside your house, contained in the compressor condenser unit outside your house that might be serving your heat pump or your air conditioning system. This is a couple of examples of a positive displacement air compressor. over here, look, we've got two pistons and cylinders here operating in series. It's called a two-stage positive displacement compressor that might be in a machine shop or your workshop downstairs or something like that, compressing the surroundings air up to a potentially pretty high pressure. Now, this is a static view of a GIF file that does a great job of showing the piston and cylinder operating at a certain speed. So the GIF file is showing the operation of these two air compressor valves, okay, that's admitting a volume of outside of surroundings air. It's compressing it. The next valve opens and squishes it out to the outlet state. Now, so wow, that looks a lot like a problem from Chapter 1 and Chapter 2, doesn't it? Well, when the air positive displacement compressor is running at a steady rate, it's really kind of in the whole scheme of things, sometime as you go, but from lunchtime to dinner time, you can imagine that the flow rate of the incoming air is sort of a constant value. That would be kind of like steady state, same thing on the discharge, steady state, steady flow. So in the whole scheme of things, we've got a constant flow of air coming out, a constant flow of air coming in. They exactly match. So we would model this as a steady state, steady flow situation. Here's an example of an axial gas compressor. Now, the application here is probably compressing natural gas that's being transmitted through a very large natural gas pipeline for miles and miles. So this would kind of be one of the casings removed. And so you see visually, I've got, let's say, natural gas. We would treat it as an ideal gas coming in, and you see multiple stages connected to the shaft. And of course, this would be the drive shaft. In this case, I didn't show W dot. And of course, the outlet would be going, so let's say to the pipeline. This is a wonderful view of an axial gas compressor rotor. In other words, the rotor pulled out of its housing. And this gives you a real good view of the inlet volume coming in, necking down, necking down, necking down. So the specific volume is decreasing. That means density increasing to this much smaller outlet area. And this rotor here, so the fellow here is touching this brass rotor. And so you can see that what comes out, the compressed gas then is going to be spun out centrifugally to go to the, let's say, natural gas pipeline. Great look at an axial compression process. So what's your sketch going to look like? No matter what kind of compressor you have, this is what your sketch ought to look like. So it kind of makes sense. I've got an inlet state 1, outlet state 2, one inlet, one outlet, open system, steady state, steady flow. So in the generic sketch, we've got Q dot in and W dot out. Notice here on my sketch, I am showing W dot out, but I'm showing it less than 0. I'm clearly writing less than 0. In my world, I never write W dot in. You may get a little different guidance, but I'll tell you that in my world, I maintained my student sanity because my professors taught me always use W dot out and then denote it with a less than 0 sign for things like compressors or pumps. You'll also see that I've got a Q dot in. So in the generic situation, you've got Q dot in. In many situations, kind of like that industrial air compressor I've got experience with, that compressor casing is going to be it's going to be insulated. And so imagine fully insulated. So the synonym for fully insulated is adiabatic, meaning no heat transfer. So you may read in a problem statement, a fully insulated compressor. That tells you the process would be adiabatic, or in other words, Q dot in. If that were the case, you might draw Q dot in, but in your sketch show equal to 0 if it's adiabatic. Okay, so hope that helps you get some clarity on what would my sketch look like if I have a compressor in my problem. Oh, well, and so you see how it necks down, right? So I'm trying to show a trapezoid with decreasing specific volume. That's why I show the shape of the compressor more than a cloud or a box or a circle or something like that. I show the trapezoid to show other engineers and remind myself that I've got decreasing specific volume. The continuity equation can help you. And that, lo and behold, all I did from the previous video was copy and paste the slide, and I changed my sketch. Always have your sketch available. And what I've done is I've observed that, well, M dot, steady state, steady flow, M dot is rho 1, A1, V1, and that equals rho 2, A2, V2. You've got the drill on lots of combinations for this fundamental to solve for. And I did make a note that in compressor situations, a commonly given piece of information, commonly given, is the inlet volumetric flow rate. And so, for example, A1V1 is commonly given. And if you have air, you'd better be, you know how to calculate rho 1, or similarly, you know how to calculate V1. So do you see that commonly for compressor problems, volumetric flow is given, you compute V1 or rho 1, and you determine what the mass flow rate is. That's what you do as step one in problem solving for these compressor type problems if you're not given the mass flow rate. Now, same idea, copy and paste the turbine slide, except change the sketch. This is exactly the same first law of thermodynamics for an open system, steady state, steady flow, one inlet, one outlet, that I presented for the turbine. Exactly the same. It's copy and paste. And so one thing you do want to see, right? So I hope you're getting the picture that this is not a formula for a compressor. The other identical one was not a formula for a turbine. It's the first law of thermodynamics for steady state, steady flow, one inlet and one outlet, open system. So I hope that helps. So do you start to see the drill that there's some fundamentals associated with all these different pieces of equipment, but you'd have a tough time maintaining your sanity if you think that these formulas apply to specific pieces of equipment. So I hope that helps, and stay tuned for the next piece of equipment that I'm going to cover here in the next video.